Hello, everyone. Good morning. Welcome. On behalf of the Victorian team at the Institute of Architects, I would like to offer you a warm welcome to today's lean-in. We will be looking at keeping your building thermal bridge free today, something which I'm quite passionate about myself, so I'm really looking forward to this session. My name is Mark Bernstein-Husman. Some of you might know me. I'm director at Melbourne Design Studios and also at Hood Sustainable Building Supplies. And it's my honor to be your host and moderator for today's lean-in session. We are joining from across the country today. We acknowledge with deep respect the traditional owners of this land. We acknowledge that it is a privilege to stand on country and walk in the footsteps of those before us, and we pay our respects to elders past, present, and emerging. Today's lean-in session is being recorded, so if you miss anything today or if you have to leave early, we will be publishing this recording on the Institute's YouTube channel in the next couple of days, and the Institute will share that link with you in upcoming email communications. This lean-in session also enables you to ask questions of our speaker. So if you have a question or a comment, please use our Q&A box down below to add your question, and I'll go through these with the panelists later in the session. I'm personally really looking forward to today's session, which will feature one panelist, Elena Cazacu, sorry. Elena is a director at Evissa. She's a passive house designer, a registered architect. She's passionate about building physics and passive house. She's been holding different roles with exposure to a variety of projects across small to medium scale practices, working with architects, non-for-profits and developers from both public and private sector. And now she's focusing her profession on healthy buildings delivered to passive house standards, which is a great thing to do, of course. For that, she uses modular structural insulated panels, also known as SIPS panels, and seeing the opportunity to improve the Australian housing stock through effective, sustainable strategies, she established Evissa in 2017 in partnership with a domestic and commercial builder. Elena will share her knowledge on thermal bridging with us today, and we're very thankful and excited about that. Elena, welcome to our lean-in, and great to have you with us. Over to you.
Thank you, Mark, for your introduction, and good afternoon, everybody. Also, thank you for choosing to spend your lunchtime with us today. It is pretty wet today in Melbourne, and I'm happy that you chose to spend it with us. And I'm happy that it's not sunny, so you don't have to trade your lunch break, sunny lunch break, for your attendance on our webinar. But I do hope you'll find the presentation on the thermal bridging valuable. And some of the objectives we will be covering today are linked to explaining what is a thermal bridge. We'll show a few examples of thermal bridges and go through discussing conductivity and resistance for a number of materials that are used extensively across to create our building fabrics. We'll have attempt to unlock the myth and how to calculate a thermal bridge. We won't go in greater depth as it is quite a complex exercise, and Passive House does cover that quite well in their courses. Essentially, thermal bridges are linked with Passive House. That is considered to be best practice when it comes to achieving well-insulated dwelling and well-insulated building, we should say, because it's applicable for both dwellings and commercial constructions. Some of the tools to assess a thermal bridge and some of the software and programs available to assess thermal bridges, the impact that thermal bridges have on our buildings. We'll also show a few examples of some of the materials and products available to achieve thermal bridge-free construction, and list a few rules of thumb on what to do at design stage, early days design stage, so that you can overcome the occurrence of thermal bridging. We will be using a few building physics jargons, such as I mentioned before, conductivity, thermal resistance, psi value, chi value. Please do make a note of them, and I'll do my best to cover them at the end if you've got questions on the specific terminology that we will be using today. So thermal bridge is essentially a change in the thermal envelope where the energy flow is altered. In most cases, the thermal flow or conductivity is significantly higher when compared with the surrounding areas. Unfortunately, thermal bridges are invisible and often overlooked at design stage, and are generally the main component of building physics principle causing severe damages to the building fabric post-occupancy, particularly with the buildings that are achieving high levels of insulation. Simplistically, the more we insulate, the higher the risk of thermal bridging occurring. The image in the slide is showing a series of linear thermal bridges occurring alongside the stud frame of the walls and across the windows areas. The windows in this instance could be actually classified as a surface thermal bridge, even though the terminology surface thermal bridge doesn't really exist. We will see later on that there's mainly two main categories of thermal bridges, but windows play an important role in making or breaking a building fabric of a building. The photo is, I should mention also that the photo is taken using a FLIR, which is a FLIR thermal camera. Often when we refer to the thermal bridges, we can identify them in two main categories, as mentioned before. So there's a point thermal bridge, and it's shown onto the left-hand side of the screen. And they are caused essentially by penetrations or elements like steel beams, surface penetrations, nails, metal profiles protruding through the building fabric, screws, and other similar elements that have essentially a higher thermal conductivity than the material they are penetrating through. They are called chi values. I remember in Europe we used to call them psi values. We'll just use chi, I think, so because some of the people in the room that are passivhaus designers may be familiar with that terminology. The second category is the geometrical thermal bridges, which are often seen as a linear shape, but we do see them in surface, as in when we refer to the windows, for instance. It can occur as a surface thermal bridge as well. But the linear shaped thermal bridges are occurring at the junctions of two elements having the same or different conductivity. So, for instance, the protrusion of a balcony, which can be seen in the image, the slab edge or a ridge beam, these are called psi values. And both the coefficients, the coefficient for point thermal bridge and linear thermal bridge are shown into the screen. So thermal bridge being a high conductivity pathway within the building fabric is actually caused, so the cause of creating this high conductivity pathways are the materials that are better conductors of heat and are allowed to form the bridge between the inner and the outer phase of construction. This commonly happens where there is a gap in the insulation layer. So air gaps are also classified as thermal bridging, where an element such as a joist is penetrating through the building fabric, a metal beam that cantilevers outwards to support an overhead volume, or it can also be an edge of a concrete slab, as mentioned before, a balcony, or a steel anchor. So we're showing there some of the some images or some examples of where we should look for thermal bridging in the built, as well as in the built construction, in the erected construction, but as well as in design. So if we're using a 3D modeling software, you could easily identify them when you are, for instance, coordinating the engineering with the architecture. So we're referring to some of the steel members that are generally used in design. In relation to material conductivity, this is defined, and this is going to be quite technical, but the material conductivity is defined as the ability of a material to conduct heat from one side to another. So it is represented by a coefficient called lambda that is essentially outlining the thermal conductivity of a material. Lambda is expressed in watt per meter Kelvin, which translates into how much energy flows through 1 meter of material at 1 Kelvin temperature difference. The smaller lambda indicates that the material has a stronger heat insulation capacity and preservation, and is achieving a higher resistance, commonly known as R value. So that is lambda there. We can determine the overall conductivity factor by knowing the R value and the thicknesses of each component of the wall, floor, or roof system. Equally, we can calculate the R values, which are essentially the reverse of the U values, knowing the conductivity and the thicknesses of the layers used to create the building fabric. U value essentially represents the conductivity transfer. R value represents the resistance in the face of the heat transfer. So the image in the right-hand side corner is actually showing how we calculate the lambda coefficient for 120 millimeter thick insulation of, I believe it's glass wool. So that is utilizing the R value, which is the 3.6 square meter Kelvin per watt. So that R value, so the depth of the material is divided by the overall R value of the material, and in the length of 1 meter or 1 meter thickness, and it's giving us a number 0.033 watt per meter Kelvin. Pardon me, watt per meter Kelvin, which is essentially I hope it's essentially a familiar U value for an insulation that you would have seen before. We're also listing down the material conductivities for some of the materials that we use in our building fabrics. So aluminium is quite high, conducts energy quite fast, steel as well. And then when we go to timber, OSB, those the conductivity levels drop, which is a good thing. Glass wool also is a very good insulating material. Neopor as well, a very good insulating material. So we want the conductivity levels to be really low, or the thermal resistance to be really high. Now, we'll attempt to have a go at understanding how we calculate thermal bridging, but we won't go into too much depth on how we calculate them manually. And I'd just like to only mention the two formulas used to calculate the heat losses caused by the two types of thermal bridging. The information we need to have available for this is the length of a thermal bridge. So the linear thermal bridges are actually measured in a linear. So if we, for instance, think about a ridge beam, that is holding a roof together, the whole length of that ridge beam could potentially be causing a thermal bridge. So that is classified as a linear thermal bridge. And then when we refer to the point thermal bridging, we have to calculate the number. So for point thermal bridging, we have, as an example, a good example would be a beam that is protruding through the building fabric. And then we have to also consider the point thermal transfer for each psi value if it's linear, or chi value if it's the point thermal bridge. There's also a correction factor. Again, I won't go into lots of details here. And there's the heating and cooling degree hours, which are available to be calculated depending on where the project is located. So in Melbourne, the heating cooling degree hours would be different from Sydney, or it would be different from Europe. As an overall requirement, the thermal bridge a thermal bridge free construction should be the sum of all of the linear thermal bridges across the whole building fabric, and the sum of all of the point thermal bridging, again, across the whole building fabric. And that should essentially be very close to 0.01 in passivhaus environment. So for those who are interested to go in detail to understand how to manually calculate a thermal bridge, passivhaus course covers this subject into a greater depth and explains in detail the building physics behind the phenomenon. And I do strongly recommend this course because it's fabulous the way it's presented, and the Excel passivhaus planning package is a great tool to be able to determine how your building fabric is performing, irrespective if you're aiming or not to achieve passivhaus certification for a dwelling. I believe it's best practice to get it right from the very start of design process. And the important aspect to remember here is that the main reason we calculate the thermal bridges is to determine what are the heat losses and gains occurring through the building fabric, high risk areas, we call them, and how to reduce and eliminate the condensation risks in those high risk areas. As said before, the overall sum of the all of the point and linear thermal bridging needs to be very close to 0. And when we're achieving that, we can say that we have essentially achieved a thermal bridge free construction. As you know, some of the people in the room may know, a thermal bridge free design is one of the 5 fundamental principles of the passivhaus design and construction, but also a concept that has been in Europe around available for a while. And I do remember when I'm practicing architecture in Europe, in Romania, it was actually compulsory to run dew point analysis and determine if the building fabric has any thermal bridge high risk areas in design. So through the design phase, that was part of the mandatory requirements of having our projects assessed in that respect. And I do believe in Australia it can be an ideal exercise that NATES or NABES assessor can undertake for our projects. And hopefully we aren't too far until this becomes compulsory. It's just a suggestion, but I believe they are important aspects to be considered, as it can make or break the comfort levels of a building. The 2 examples shown in this slide represent a section detailed cut through a balcony. The one on the left-hand side has a very thin layer of insulation across the walls, if any insulation. I think it's very thin. And the balcony is extending across the fabric. And the one on the right-hand side assumes a similar scenario with a well-insulated outcome. So both the walls from the top and bottom and the balcony itself, I believe the balcony is CLT. So the right-hand side assumes a better scenario in terms of the insulating outcomes. And now looking back to the passivhaus standard, we should mention again that the thermal bridge free design represents and requires for the psi values to be close to 0.01 watt per millikelvin. And we also know that the interior surface should not be lower than 13 degrees, actually 12.6. And looking at the example on the right-hand side, it could be a bit confusing because the thermal bridge result is actually higher than the uninsulated example on the left-hand side. This happens because thermal bridge is actually calculated to represent the impact the additional insulation has on the overall value of the thermal bridge coefficient. One could look at the calculation and think, why are the thermal bridges worse in my insulating building? The thermal bridge for the uninsulated wall has a result of 0.24, so one could think that that's actually performing better. And then the thermal bridge in a passive house, so the right-hand side example, has a result of nearly 3 times higher, so 0.69. This is simply because the way the thermal bridge coefficient is calculated, the linear heat loss coefficient is relative to the undisturbed component and signifies the additional heat loss caused by the thermal disruptance, which essentially in our scenario is the balcony delivered with CLT, which has a higher conductivity than the insulation utilized into the wall. And it's quite complex, but simplistically, if we were to draw a conclusion and have an observation, for the case of the uninsulated walls, the heat loss is very high. So the situation is hardly worsened by the projected balcony, as we're losing a significant amount of energy on all sections of the building fabric, namely the walls and the balcony and its own protrusion. The heat, the heat losses are 98.5 watt per meter, and so that's quite a high number. And when we're comparing with the passive house, this is significantly dropped to 4.76. So we're, obviously the right-hand side example is the good practice one. So if the wall is well insulated, then the energy loss through the uninterrupted wall will be lower at the balcony slab, and it will then impacted by the significant deterioration caused by the CLT component protruding the building fabric. And then the balcony becomes the actual thermal highway or the thermal bridge. While it appears as though the thermal bridges are worse in the right-hand side example, showing improved insulation, the total heat loss is obviously considerably reduced by the insulating measure, and the temperature of the interior surface is increased to a greater than the critical level of 12.6. So we see there that the surface temperature is 14.1 degrees Celsius. And in that scenario, we can assume that the dew point is situated within the warm part of the insulation, achieving a low risk of mold development within the normal indoor air humidity levels. So indoor air humidity levels in this scenario are 58.71, and an overall temperature is the 21 degrees. As a conclusion to just this particular side, we are essentially creating the thermal bridges due to the need of becoming more efficient. So the higher the insulating levels, the higher the thermal bridge risks are. And even if we are looking at thermal bridges that show high values of heat transfer, it's important to remember that is the difference between the insulating component and the component that creates a disturbance into the insulating path. And also surfaces are also important to be assessed, as if they drop below the 13 degrees, that cold area could create condensation and later on mold development. Another important thing to remember about thermal bridging is that the thermal performance of the building fabric should achieve a continuous insulating layer across all sections of the walls, floors, and roof, including protrusions, balcony areas, windows, doors, bridges, and other critical connections. This may not be a new concept, but is essentially one of the most important things to remember when it comes to designing building fabric of a building. So we're again showing some U values, some thermal conductivity values, which are generally required in a passivhaus application. It should have roof walls and floors. Roof and walls should generally be seated at 0.15 watt per square meter Kelvin in terms of conductivities, and floors 0.25 watt per square meter Kelvin. It all depends if that floor is a suspended floor or if it's a floor on ground. If it's a suspended floor, the U value would have to be lower. And also for windows, we're showing a U value of 0.8 watt per square meter Kelvin, and that is a very low U value for a window. That window is a high performing window that would probably have a triple glazed component. It may seem the U values that we are showing, they may seem conservative or maybe too conservative, but through practice we have noticed that if the design allows for a substantial area of glazing, for instance, if we were to just consider the windows, we will need to insulate, we will need to increase the performance of the window. So if the overall area of glass into a building fabric is, I think in passivhaus environment is generally acceptable to be within the 20% of the overall building fabric. So if we have a small amount of glazing, we will probably going to be able to have higher U values for windows of 1 or 1.2, 1.6 in some areas. It all depends of their size and orientation. Solar radiation is also very important. So as mentioned before, passivhaus recommends to consider 20% glazing area out of the overall building fabric, especially for domestic projects. In commercial projects, it's slightly different because the volumes, the internal volumes are higher. We did notice that even with our designs, this ratio isn't always in favor of the opaque areas. So the windows and external doors sizes can be quite large at times. And we do have to use then windows that are have lower U values. And I suppose to accurately assess a thermal bridge, we don't even, us in the practice, we don't actually calculate thermal bridges manually. We use the passivhaus planning package, and we've got a program, HT Flux, that Teresa has recently looked into working with. It's worth mentioning that Graphisoft, if there's any ArchiCAD users in the room, Graphisoft has a very basic tool in assessing thermal bridging. So it's worth having a test to see how the building fabric behaves. If you cut a detail into the building fabric, you'll be able to create and model a quick thermal bridge in ArchiCAD. They're not as sophisticated at Flixo, at HT Flux, or other similar programs, but it will give you a good understanding on how the heat flows behave and how the heat flows, I suppose, perform into the across the overall walls, floors, and roof. And I'm not sure if Revit has a tool like this. I'm not a Revit user, but I know ArchiCAD has one, and I've found it quite useful. Some examples of the materials and products that are accessible on the market to be used, and we did use just recently the Shock Isocope product, which is this detail, and we've installed it into a steel beam that was cantilevering out of SIPS building fabric. And it can also be used to along the line of the balconies and any other cantilevering construction elements which project through the thermal building envelope. The example at the bottom is called the Shock Novamur. It is a thermally broken load-bearing insulating element which is used around the entire perimeter of the building's foundation and slab to ensure thermal disconnection between the building and the earth is achieved. And obviously, for domestic application, we have the modular system structural insulated panels that can provide thermal bridge-free building fabric if the system is used mainly in conjunction with timber framing. Even in the projects that we're delivering, we find at times that steel is necessary. Some of the designs are quite bold and elaborated, and we do like design, and we want to obviously maintain the architectural outcome at the top. We don't want to put passivhaus at the top. Architecture is important, so we want to keep the designs, and we do believe that any building can achieve a good building fabric irrespective of the way that it's been designed. In saying that, though, some of the buildings can be a bit more challenging than others, so obviously a simplified volume will achieve an easier solutions when it comes to building physics, passivhaus, or resolving thermal bridging. I'd like to maybe add quickly here a concept that is probably not as relevant to the thermal bridge, but it is important to understand how the energy transfer occurs. The heat is the one that moves through space and follows the cold, and essentially it's taking its place. So it's always the heat that moves, and it's never the cold. Heat will always follow, heat will always want to follow from hot areas to cold ones. And in doing so, it follows the path of least resistance. So we've seen before the example with the balcony, that was the balcony, the CLT balcony was essentially the path of least resistance. If that balcony would have been a concrete balcony, that would have been a thermal bridge, and we would have had a really low temperature at the internal surface. So the heat highways are headed straight into the cold areas, indoors during the summer and outdoors during the winter. So across the summer, thermal bridges are responsible mainly for heat losses or heat gains, if we were to consider the heat that comes inwards, and less likely to create condensation and mold development. This later phenomenon is more likely to happen during the winter. Usually the indoor surface temperature near a thermal bridge is lower, and if this spot becomes too cold, below 13 degrees in the passivhaus world, it could lead to condensation and moisture buildup. So we've seen before in relatively short periods of time, even 2 or 3 years after a building is occupied, the mold will start to develop and can have potentially damaging effects to the building structure, not to mention the health hazards on the occupants. For all existing buildings, we could use thermal cameras to detect thermal bridges, even before they become visible in a form of condensation and mold. So during construction, we find this is a very useful tool to have, as we can closely monitor the high-risk areas. So in the photo, I'm showing an example of a FLIR device, which can be used with a smartphone. We do have one of these devices in the office, and I find it quite useful because you can easily connect it to your phone, and it's fairly cost controlled. Some of the FLIR equipment can be quite expensive, and I'm sure they are necessary in larger commercial projects to be used. So in planning for a thermal bridge free construction at design stage, I'd like to all consider the following things, which we believe are quite important to remember when we again plan for a thermal bridge free envelope. One thing that has been said before, a continuous insulating layer without gaps on all our sides of the buildings, from floor to walls to the attic space to the ceilings to the roof areas, all of the sections, irrespective of them being opaque or solid, they need to achieve a continuous insulating area with internal surfaces in the passive house world not less than 13 degrees. The windows and the glazing components should always stay within the insulating areas, ideally placed in the center, but not outside the insulating component. Utilize thermal break materials if you need to interrupt the thermal transfer that comes through steel members or metal connections or concrete slabs. Use materials that have low conductivity values. So this could be a decision that is made in early days design process. You could use timber over steel to deliver your overall frame for the building is also sustainable if the timber is sourced in a sustainable way. Avoid metal protrusions, as mentioned before. Simplify the building geometry, and I know this is easier said than done. We have mentioned this today because a simplified building geometry will essentially achieve a more cost-effective outcome, but we don't always want to utilize only simplistic building geometries. Sometimes more complex designs that are more suitable for particular contexts should be allowed to be considered. So I do believe that any building fabric can be delivered, provided that the costs allow. Any building fabric could be delivered to achieve a zero thermal bridge free scenario. Documentation, obviously, it's critical. They need to be precise and well detailed, and all with using lots of sections. You can have 10 or 20 sections across a project that will essentially look at all the critical aspects in connections from top to bottom, left to right, east to west, north to south. So documentation plays a very important role. And this is probably a note for the designers and the builders: do not penetrate the installation with services and connections. So through the design, all of the services reticulations could be organized in such a way they are mainly reticulated indoors within the internal walls and less exposed to the outer building fabric, to the external walls. And also we have seen even, on our sites, in our projects that we deliver, the subcontractors need to be educated that every penetration that occurs in the building fabric, through electrical and plumbing, or ventilation, or HVAC, that will create essentially a thermal bridge. So they need to be taped and sealed to be able to eliminate them. And least but not last, build airtight. So air gaps in a building fabric are essentially thermal bridges. So the more airtight we are, the better the outcome. And I'd probably like to conclude here, and I'm probably running a little bit behind schedule, low on time, but this is just an example of a detail used in a building fabric delivered with our modular system, structural insulated panels. And I only want to flag here all the aspects of the building physics which are important to be considered in design. We know already that having a thermal bridge free construction is only one singular element out of many. So airtightness is also very important. Having a continuous insulating layer is very important. High performing windows, well ventilated indoor spaces, as well as well ventilated cavities is just as important, and they shouldn't be left behind. So everything has to be seen as a whole when we plan, and we shouldn't plan only to have a thermal bridge free construction. We should actually plan to have a building fabric that considers all of the building physics requirements. I'd like to thank you now for your patience in us delivering this webinar, and also I'd like to thank Teresa Branch for our office who helped me put this together. She's also passivhaus designer, and we work together, and she's a fabulous person. I'll finish here, and if there's questions, I think there's a few questions we could start taking, and I'll try my best to respond.
Thanks. Thanks, Elena. Wonderful presentation. Really enjoyed it. There's quite a few questions from the audience, but if I may, I would like to start with a question of my own. I think you've really brought your passion across for healthy buildings and for the importance of building physics and thermal bridging. Do you feel having that knowledge makes a difference for you as an architect? And do you think as architects embark on the journey to deepen their understanding in those subjects, will they experience a reward in terms of customers and clients that are also more geared towards better buildings, or why should they do it?
Yeah, that's a very good question, actually. And I suppose, like yourself, we've are trained as architects in Europe. So we've followed architecture school delivered in the European format, and building physics topic was quite intense during the architectural school years. We remember I had a course every year. So from year 2 to 3 to 4 and 5, there was a building physics project or technical project or a building physics course, related course. And that helped a lot, I suppose. It did create a good, solid, and helped, help myself, and I'm sure you can relate to that as well. Helped us understand how materials behave when they are utilized to create our buildings, building enclosures. It's worth mentioning that I'd like to, future generations, and I do hope that building physics topics and subjects are introduced in the architectural schools in Australia. I actually have recently noticed that even from the school I graduated from, some of my colleagues have mentioned that they are trying to reduce the building physics courses because they are too complicated, they are too complex, which is not something that I want to see. Obviously, definitely not in Europe, as they do represent a good role model for us. But I suppose I mean, to answer to that, I believe having a solid base of and knowledge of physics and understanding how materials behave when they are collated together to form a building is quite important. And I'm not sure that answers, but
no, that's great. That's great. There's some questions around technicalities and some questions that are a bit broader. So I'll just jump in there. Someone has asked, does the dew point change with building classes, say between class 2, 3, and so on?
Dew point change with building classes. I actually probably not going to be, I'm not qualified to probably answer that question because I mostly navigate in domestic world. I would say it does because it is influenced. So, you know, holistically, the building fabric is also influenced by the amount of volume that it contains. So, the larger the volumes, the internal volumes, the easier it is to achieve comfortable levels and the easier it is to achieve passive house. If I could, I would like to get back and I'd like to search a good answer for that question, and I will endeavor to get back to you with an answer after this, if that's possible. Again, I think I've got the answer, but I don't want to give the wrong answer. So
thanks, Elena. That's great. Jeff says, Elena, great presentation. When I look around at the design of residential apartments, I hardly ever see thermally broken balconies. Are you starting to notice much in the way of meaningful change in the industry? And what do you think what do you think it will take to shift the industry to eliminate thermal bridges?
Adopt the Shock Novamur product. They're not expensive. Honestly, they're not expensive. We have utilized them in a number of times in our buildings. It doesn't cost a lot to be included into the documentation. I think, you know, if it's specified in the design, it's very likely to show up on site. So make sure that the thermal break details is accurately specified in the architectural documentation, and the builder is well informed that he will have to, or they will have to include those thermal blocks, thermal break blocks into on site. That, I mean, simplistically, I mean, that I think that could be the strategy, but apartments do struggle with ventilation as well, and that's not necessarily linked to thermal bridging, and I think that's probably a more stringent cause, as all of the inhabitants in apartment buildings are exposed to indoor air quality levels that are health threatening. So for apartments, ventilation probably at the top, thermal bridging can be resolved because there's a lot of materials available on the market. And one is the one that we've mentioned today. We have no connection with them. We just love that product because it doesn't, it's easier to install and it doesn't cost an arm and a leg.
Definitely, yeah, that makes a lot of sense. There's a few questions around airtightness and natural ventilation as well. For example, David asks, how do you introduce natural ventilation into an airtight building, which goes beyond the subject of thermal bridging, but I guess it's all sort of within building physics, building science, it all comes together.
Yeah, so natural ventilation obviously will occur, opening a window and having, cross ventilation, east, west, north, south windows that can be, open concurrently. It's something that we have noticed because we installed indoor air quality sensors in the dwellings that we're delivering, and we have noticed that if there's a missed opportunity to have had a ventilation system installed into the dwelling, especially during the night, the carbon dioxide and volatile organic components do build up at significant levels. So that it's showing us obviously that the users do not actually operate those windows, even though they say, and you know, at design stages, and you know, when they move in, that they will operate them on a regular basis. That actually, you know, doesn't happen, and we've seen that, you know, while monitoring the indoor air quality levels. So in theory, yes to natural ventilation. That is essentially going to work. However, we are reliant on the users to operate them on a regular basis.
Very good. There were a few questions around the FLIR imaging and the thermal imaging that we've seen, and how the thermal bridges present as ghosting. What is that ghosting that we see? Is that a health risk? Is that mold? Is that dust? Like, can you just briefly expand on that?
It's probably, I should probably go to the image at the very start that we've used in our presentation. And I suppose if we look at the diagram, we'll see there's a legend at the bottom of the image. So the heat loss, so the brighter colors, the red and the orange and the yellowy colors, show the significant amount of heat loss that is occurring through the building fabric. And the darker colors, the greens and, you know, going to the blues, those areas show a reduced amount of heat loss. So essentially, if we look at that photo, the darker areas are a good sign. That means that we've got insulation into the roof and to the walls, and we also we've, you know, the owners have done a good job in insulating their walls and roofs. However, the timber stud frame or metal stud frame, actually I don't know exactly what that is showing signs of greater conductivity. So they are essentially seen as thermal bridging. And windows, they aren't very well performing. So windows are probably, you know, the worst component of this building fabric. So I'm not sure if that answers, but you know, simplistically, that's how we would navigate,
I think that makes sense.
the thermal bridge image. Yeah.
Yeah, I think that's good. Rod is asking, are any of the software options that you've mentioned better than others for identifying interstitial condensation risk? I mean, in our office, we use the Ubacus calculator, which is an online tool, which I think is fantastic for that. Yeah. But yeah, question to you.
Yeah, I know Ubacus. It's actually great. It's got so much, it's got a great library behind it. Flixo, it seems to be very popular. HT Flux is a bit more basic, I suppose. It all depends. I mean, they come at different costs, all of the software. To be honest, I wouldn't want to recommend one over the other. I have used Flixo in the past, and HT Flux recently. Teresa is using it in our office, but in the way we design, I suppose, you know, through our, you know, when we deliver our projects, I am an ArchiCAD user, and ArchiCAD does have a great tool to quickly run thermal modeling. And I quite like that one. And I know it's probably not showing all of the information relevant to, you know, and required for passivhaus certification, but it's good enough to show if we are or not dealing with a thermal bridge. So I don't want to recommend, I suppose, programs, but I just, you know, maybe just have a trial of, you know, a month. Most of the programs do come with trial periods, and, you know, test to see which one works better.
There's a few more questions around ventilation and a hermetically sealed box, which takes the discussion sort of away from this. So I think we might leave them aside for now, because that's more a discussion around passivhaus and how do you ventilate properly and all those things. Is that right, or do you want to make a comment on that?
I do, yeah. So what was the airtightness that comes with so in relation to
Yeah. Well, one of the questions was, it would seem that the aim is to create a hermetically sealed box. How is ventilation resolved?
Yeah, well, the problem, we have to do that because we have to be energy efficient. If we were to leave the buildings to leak everywhere, as in air leakage everywhere, we would essentially be living in healthy buildings. However, we would pay a fortune on the energy bills. So the problem with thermal bridging and airtightness is we are actually creating those problems through the design because we have to be energy efficient. And that is, I suppose, the situation. Historically, if we look at buildings that are 100 years old, even some of the buildings delivered in Australia that have been delivered to good craftsmanship and well built, they are standing proud. They may need considerable amount of refurbishment, but the framing, the timber framing, if it's had the opportunity to be self-ventilated on a consistently across the years, most of the times is intact. And we get involved a lot in heritage dwellings, for instance, and we see it all the time. Once you remove the weatherboard cladding or plasterboard, the timber frame can be preserved. However, those buildings are very cold in the winter and very uncomfortable when the temperatures peak either to 0 or they go to 40 degrees. So the aim, I suppose, and the industry aim and the climate change aim is to be able to save on the energy bills and increase our comfort indoors. And that's when all of the building physics methodology comes into play. So we're actually creating these problems. They haven't been inherently existing into the old buildings. We are creating them as we're hoping and we're trying to become a bit more energy efficient. So being zero energy bills and having zero energy bills for a home is essentially achievable just by aiming to achieve passivhaus standards and relying on a small renewable energy system. So I've probably digressed a bit, but yeah, so air tightness obviously is one of the components of the building physics that is important to be considered. An airtight enclosure is essentially a thermal bridge free enclosure. So an airtight building will essentially have a very small amount of heat losses through the building fabric, and it will create, with additional ventilation and mechanical ventilation, it would create healthy outcome for all the inhabitants. And I suppose if I could just add there, we haven't, we're going into summer soon in Melbourne, and we did have the bushfires a number of years ago, and an airtight building could have been fantastic when all of the smoke was around us, because they are obviously going to be able to preserve the indoor air quality to better levels when compared to outdoor pollution, for instance. But that's, again, we're digressing, but yeah.
Yeah, I agree. I mean, I live in an airtight building. I live in a passivhaus, certified passivhaus, and I invite everyone who's sort of on the fence or doesn't really believe in it. I invite everyone to send me an email, and feel free to come and visit the house to experience what it is like. It is amazing if it is well designed, if it is thermal bridge free, all those things. It's a healthy building, and it feels really, really nice to be in those buildings. So it does make a huge difference, I personally believe. I think we're running out of time. There are a few more questions. So I don't know if we want to keep going with one or two, or if we just want to
that's fine. If people are that's fine, or if if we can take them even afterwards via the email. But I'm happy to spend a little bit more time to if people are
sure. There was a question. You were showing a beautiful detail with quite a lot of information in there, and there was one question around that. If you could elaborate on how specifically you achieve the thermal bridge free construction within that detail, like what does it make a good detail?
Is this the one? It could be this
I
one.
think so, yes, yeah.
I particularly chose this one. This is a detail that was actually developed by Pinto Tuncher, with working with their architectural practice, and we have our modular panels specified for their project, and they are hoping to achieve passivhaus standards. And unfortunately, the engineering design got a little bit too conservative, in my opinion, and some of the steel components were, I suppose, specified through the design, so we couldn't actually design them out. And we've come up with, strategies to keep them away from, protruding into the building fabric. So I suppose, it's sort of, the detail is cut in a funny way, but we imagine that this is the indoor component of the dwelling, and that is the outdoor. So left-hand side, indoor, outdoor, and that is a box gutter there. So that is, I suppose, an angle holding the roof, and it's fixed onto the lintel that is then supporting a window. What's interesting to observe here is that the steel does not protrude all the way through the building fabric, so it sort of stops halfway in the middle, and there's enough insulating material around it so that steel component does not create a problem. And then there's a number of red and blue dotted membranes, which the red line is essentially outlining the airtightness. So airtightness is always a component that will occur internally, so within the internal face of the building. And the blue material is a vapor, what we call a vapor permeable membrane. Another thing to, I suppose, mention is ventilation and ventilation cavities. So there's two types of ventilation, and one is, ventilating the internal indoor air, so the air that the occupants breathe, essentially. But we should not, I suppose, leave outside the ventilated cavities. So how did the materials ventilate themselves? As in this scenario, for instance, we are dealing with a brick veneer finish, and the brick veneer is considered to be a cold finish, or a finish that is actually holding moisture content. So there's very, it's likely for this material to be releasing condensation onto the back. And that 40 mil cavity is, I suppose, we need to make sure that that is continuously ventilated, and the membrane is always allowing to capture any potential condensation that could occur from the brick, from the layer of brick veneer, is allowing for that condensation to essentially be drained out. So we'll see there's a flashing, and the metal flashing is actually drained onto the outside through a vent, and the blue membrane is covering the flashing. If we would have had metal cladding there, it would have been a similar scenario. So ventilated cavities, very important to be designed well in across the whole, from top to bottom, left, right, north, south, east, west. Any other particular questions in relation to these details, so that I don't just
no, I think you've explained that very well.
Yeah.
Thank you. I think that covers the gist of it. There's lots more questions that go into sort of more general discussions, costs of triple glazing versus double glazing, and all those discussions. So I guess we could keep going all day if we want to.
Yeah, I can see there's quite a few. Look, if there's any questions that we can help with, within reasonable amount of time, even after this, and we're happy to take a few questions over the email. And I believe, Teresa, this will be video recorded, and we will still have access to the information that we've covered. And Teresa has prepared a few sheets, outlining some of the takeaway points, how to design, a building, good quality building fabrics. And if there's interest, we'll pass this on to Evissa. And if there's interest and people want to have a look at some of the tactics that we've put down on paper, we're happy to share, just to increase awareness on how to improve the quality of our buildings.
That's great. Thanks, Elena.
Right.
I loved your presentation. I loved all your answers. And my biggest takeaway, I think, was along the slide with the balcony that you had. I thought it was so interesting to see that the thermal bridge has actually a bigger impact on a better insulated building, right? And that's, I think, one of the takeaways. The more we insulate and the better our buildings become, the more important all this stuff becomes, and the more important building physics and thermal bridges and airtightness really becomes, because otherwise we go through the same experiences that other countries have experienced before us, where we end up with buildings that make people sick, and we don't want that, because that experience and knowledge is already there. So thanks again, Elena, and thanks everyone for joining. Just a reminder that lean-ins are recorded to view later, so you can receive a notification of when a new lean-in is available to view by subscribing to the Australian Institute of Architects YouTube channel. And of course, you're all already subscribed to that, I assume, but if not, then you should quickly jump on and subscribe to it. There's always great new stuff coming out. Yep, thanks everyone, and have a great day.
Thank you everyone for attending. My apologies that we haven't got a time to cover all the answers. I can see there's like 26 in there. I would be happy to, help even after this. So, through Evissa, if there's a way to collate the questions, please let's, have them maybe in a Word document, and we'll try our best to provide some answers and, some, strategies and directions on, what to do in certain scenarios. And again, through Evissa from the Australian Institute of Architects, we can communicate in this way. So, so that you have, we do our best to answer to everyone's questions, given that the time is limited today.
Awesome. Thank you so much, Elena.
Thank you everybody for coming in. I think the sun is coming out soon.
Great, time to get out there. All right, have a great afternoon, everyone. Thank you.
Thank you.
Bye.